Hello everyone, my name is Gabriel Bornea. I'm a team lead in ING Tech Romania, and today I'm going to talk about a very a subject that I'm very fond of, which is functional programming. And I will try to show you a different way in which you can think about your APIs. Uh, Also, everything that I'm going to show to you today has already been tried by my team in applications that run in production. A little bit more about me. I usually code in Kotlin and in Java because most of the applications that I work on run on the JVM. But I also enjoy coding in other programming languages that are more oriented to the typed functional programming style, and these are F Sharp and Scala. I also truly believe that applications should be testable, reactive, and functional because a deterministic application removes a lot of headache at runtime. Most of the time we write APIs, and as I've said earlier in this talk, I'll try to show you a different way in which you can do that. Initially, I thought about doing a generic presentation without examples in a particular programming language, but that wouldn't have been very helpful for someone wanting to try this approach. So here we have a mathematical function, which you can read as the function f maps elements of type HTTP request, in our case, to elements of type HTTP response. And this is called in mathematics arrow notation. But as I've said, this presentation is not a generic one. So all the examples that I'm going to show are in Kotlin. And for those of you that are familiar, you might see right now that the signature is a valid Kotlin code. Uh, I chose Kotlin because I truly believe that is a great language for type functional programming. But however, Kotlin is not a pure functional language, so we're going to need some help to achieve this goal. And this help comes from a third-party library, which is called Arrow. So right now you might think, why have I chosen Kotlin if it's not a pure functional language? Well, first of all, it runs on the JVM and it interoperates extremely well with the Java ecosystem. And the code is quite familiar if you come from Java. But why functional programming? Because it's based on a very simple idea that you can build applications by only using pure functions and immutable values. And for those of you here that are familiar with functional programming, you might notice that during this presentation, I will omit some terms that are normally used in FP, but this is intentional. Okay, so what's a pure function? Well, it has some very interesting characteristics because no matter how many times you invoke a pure function with the same input, it will always produce the same output. And it also does not produce any side effects. So given these two characteristics, you can think of a pure function as a computational analog of a mathematical function. Um, okay, so what's a side effect? Well, a side effect is when a function relies on or modifies something outside its parameters to do something. For example, a function which reads or writes from a variable outside its own arguments, a database, a file, the console, even the user input is considered a side effect. And I have an example here where we have a function f, and this function f has an argument x, and it will evaluate to an f of x. And a side effect in this case would be that somewhere within the execution of this function, we would have something like this, database client, insert user. Also keep in mind, as I've said, that a pure function does not produce any side effects. But why immutable values? Well, these are also very important because they are inherently thread safe, which means that synchronization issues do not occur. And also the concurrency and parallelism given the above is easier. Another important aspect about immutable values is that you don't have to deal with mutation or state. Of course, you still need those in your application, but you can achieve them in a different way. And since we are talking about type functional programming and we're not talking about languages like Clojure or Scheme, types are very important. And while in languages like Haskell, where it is said that if it compiles, then it works, this is not true for most programming languages. But we can help the compiler by creating well-typed expressions. And in this case, the compiler can be our best friend. If our code is well-typed, the compiler is very helpful. And let's see an example. We will go through it and we will try to improve it step by step. Here we have a function that takes a string as an argument and it returns a user. How do I know what is this string? I can deduct that it's a username from the name, but that's it. And also, what's going to stop me from putting something that is not a username as an argument to this function? I could put an email, I could put an ID, I could put whatever is a string and introduce a subtle bug within my code that I will only be able to catch it maybe at runtime. So bear in mind that a username is not a string. A username is a username. And how can we address this issue? Where we could create a wrapper around the string type, but this would introduce runtime overhead because it has to do some additional heap allocation. And Kotlin addresses this issue with something called value classes. And these value classes have no identity, can only hold one value. And the most important thing is that after the compilation, this type is replaced by the wrapped type. So in our case, the username will be replaced by a string. So no more heap allocation. Okay, so we fixed this. We introduced a new type called username. But now if we look at the function, we can deduct that it's going to query by a username because the argument of the function is of type username. And I know that it returns a user because I can see it from the type signature of the function. So what I'm trying here to say is that try to avoid whenever you can. Of course, this is not possible. It's not a universal solution, but don't try to put types in the name because we know the types, we see the types, and also the compiler knows and sees the types. And maybe a good name for this function would be query instead of query user by username because the rest is deducted from the signature of the function. So we've seen how to create proper types, but we need a way to protect our business domain from invalid data. And for that, one approach should be to use smart constructors by not allowing invalid domain types to be created. So now that we've created our type username, let's see what a valid username from a business perspective would look like. So in this case, a username may be something that contains no spaces. It has only letters, numbers, maybe some special characters, and a specific length. And from a business perspective, this is a valid username. But what's going to stop me to put something like my username with a space? Absolutely nothing. The compiler cannot help me. And again, I will introduce invalid domain data. There are multiple ways to fix this issue, but I've chosen here something called an operator, which is attached to that type, and it will make sure that invalid values will not be allowed. If you look at what the operator invoke returns, it's a username question mark, and in Kotlin, this means that it's a nullable type. And you can think of it as being something like an optional of username or an option from other language of username. The important thing here is that this is built right into the type system. So I cannot treat it as a null value. I have to treat it as a nullable value, which is very good. Another good thing about this approach is that when I try to create a type username, it looks like I'm invoking the constructor. So again, it's another benefit from using this approach. But as I've said, there are other ways in which you can do it. One last thing I want to mention about types is that types can be composed. And this is only possible because there is a clear separation between behavior and data. And there are two ways on which you can achieve this. And we're going to see two examples. Let's assume we have to build a type user. And this type is going to be made from other types. So it contains one user ID, one username, one email, maybe password, and so on. In Kotlin, we can model this as a data class. And this data class is basically a type that is built from multiple types. And these are called in functional programming product types. And you can think of them as AND because they're built from something and something else and so on. Another way in which you can compose types is like this. So let's assume we have to model failures in our domain. And the failure could be maybe a database connection or a downstream service connection failure or an internal failure or so on. These are modeled as sealed classes, which are present in Java from newer versions as well. And these are important because when you have an expression that evaluates a failure, it can be only of one of these types. So now I'm building a type, but you can think of them as OR because it's a database connection failure or an interstellar failure or so on. So these are the two ways on which you can compose types, with AND and with OR. Great. So now that we've seen types and why types are important, let's see what we are going to build today. As I've said, we're talking about functional web APIs. So our business requirement is to register a new user inside our system. And in order to do this, we have to go through different steps that will allow us to do it. We have to deserialize, we have to do maybe some validation on the input, and probably we'll have to map from a data transfer object to a domain object. Then we have to insert it into our database, doesn't matter what database is. And the last step would be to take the inserted data and give it back to the client in a way that the client can understand it. How we are usually doing this? Well, I assume that most of us use Spring, and we are pretty familiar with Spring framework, which is a very cool framework because you can build something very quick. And if you go to this approach of using functional programming, it doesn't mean that you cannot use Spring. So we have a repository that is responsible for interacting with the database. We have usually services, and these services usually tend to do the business validation, insertion in the database, and so on. So it's our domain. And we have a user handler or maybe a user controller, and this is usually the part where you interact with the client. And these depend on one on the other in a structured, layered way. What we are trying to achieve today is something different because a core principle in functional programming is to use composition everywhere. And we can think of our API as being just a big function that goes from an HTTP request to an HTTP response. But this function is built by several smaller functions that do different things. And all of these smaller functions usually talk to each other in order to evaluate to our response. And you can think of them as Lego pieces that you can put together to build bigger things. Okay, so what's function composition? I'm going to take an example here, and let's assume that we have a function f that goes from a JSON to a data transfer object, and we have another function g that goes from that data transfer object to our domain object. And in order to compose these two functions, we are going to create a function h And this function is going to go from the input of the first function to the evaluation of the second function. And there are several ways in which we can achieve this. One of them is by using a lambda expression. And inside this lambda expression, we call g of f and of our input from the first function, which is JSON. And this will produce our function from JSON to user. There is a smaller way in which we can write this. In Kotlin, if you have a lambda expression with one single argument, and you do not want to give it a name, you can use the default name, which is it. But there are two ways, another two ways on which you can do this. You can use the compose function, or you can use the and then function. And as I've said in the beginning, things that are not part of the standard library and are part of Arrow will have the icon you can see here. And then it's great because it preserves the natural order of reading. So yeah, as you can see, and then is the only function that will allow us to read the composition in a natural way. So right now that we've seen how to create types, we've seen how to do function composition, let's model our recipe with proper compilable functions. We have the function register that goes from an HTTP request to an HTTP response, and then all the other functions, deserialize, validate, map to, store, and serialize. All of this is compilable Kotlin code. If you put it in an IDE, it will compile. And if we compose all of this using what we've seen earlier, our entire API could look like this. We have the register that goes from an HTTP request to an HTTP response, and inside you see deserialize and then validate and then map to and so on. This looks pretty cool, but before you have maybe a eureka moment and think that, whoa, this is very cool, there's a catch here. Types must match. So the output of a function is the input for the next. If you cannot satisfy this condition, the function composition doesn't work. And another problem here is that we said in the beginning that our store function is going to write inside a database. So how am I going to inject a database client inside this function? So in functional programming, there are different ways on which you can achieve this, but we are going to look at two principles. The first one being currying. And let's see what this means. So we have a function that goes from JSON to user request. We could rewrite it, and instead of taking only one argument, which is the JSON, it takes two arguments, the object mapper that is going to do the mapping, and the JSON. But this, if we apply this, it will break our function composition. And here comes currying into place. And what currying means is that I can create a function that takes multiple arguments into a sequence of functions where each function takes one single argument. So I can rewrite my f function like this. So right now, f is a function that takes an object mapper as the first argument, and it returns another function that takes a JSON and it returns the user request. This looks nice, but this alone does not fix our problem with function composition. And for this, we need another concept, which is partial application. And partial application means that we fix a number of arguments of a function, and we produce another function with a smaller parity. What this means is that I can create my function deserialize, and my deserialized function will take in a JSON and return a user request, exactly what I wanted. But I'm applying the function that we've seen in the previous slide with the object mapper. You do this usually in your configuration part of the application. If we were to put all of this together into our example, where we have the store function that goes from user to user, and rewrite it as a function that takes a DB client and returns another function from user to user, we can create a function save to DB, and we are basically applying the store function with the DB client. And if we compose everything again, the only thing that we need to do in order for our code to compile and to work is to replace the store function with the save to DB. So we have types, we have function composition, by using currying and partial application, but we have something called side effects that I've told you about in the beginning. If I'm looking at the signature of this function, I will definitely deduct that this function is going to insert inside the database. And this is impure because we've said that writing or reading from databases is impure. But basically, this is what we do every day. So side effects is our job. We are paid to write to databases. We are paid to read files, to have user input, and so on. So this means that functional programming is useless, and everything I've said until now, it doesn't make any sense. No, this is not true, because the whole purpose of functional programming is not to prevent side effects. It's just to push those side effects to the outer edges of our system in a well-known and controlled way. And this is where effects come into place. Effects, you should think of them as not side effects. They're completely different from side effects. We use effects to control those side effects. And now, if we think about our applications, our day-to-day application, we have the normal world. In this normal world, we have things like ints, strings, boolean, and so on. And here we have functions that goes from int to string, int to boolean, and so on. But we also have the effect world. And in the effect world, we have things like e of int, and we have things like e of string, and so on. And here functions go from e to e. They do not go from a type to another type. And in the effect world, things like option leave, things like list, things like IO, and so on. And these effects have the ability of taking things from the normal world and lifting them inside the effect world. And based on the programming language or the framework or whatever you use, you will have functions like just, like select, like lift, fmap, and so on. And effects are important, and let's see why. One of these effects is called the IO. And IO is important in functional programming because it has the ability to represent operations that are executed lazy and are not throwing exceptions until they are evaluated. And what this actually means is that the code that is wrapped inside this IO does not throw exceptions until it is executed. And the important thing is that these exceptions are captured within the IO, and we can check them in the outer edges of our system. So you could think of this IO as being some kind of a lazy feature, even though this is not entirely correct, because the IO can preserve referential transparency even when it's dealing with side effects. The good thing is that Kotlin doesn't need an IO for that, and we're going to see in a minute why not. So we have our function that goes from user to user. You could either write it like this, or you could either write it by using the fun keyword. And here I'm going to introduce something new, a keyword suspend. And what the keyword suspend does, it's basically allowing a function to be started, paused, and resumed, which is important because this means that applying a suspend function means that it requires another suspend context. And this is basically pretty similar to the IO because it is what the IO looks like when the compiler knows about it. And another good thing about this approach, and what I like most about Kotlin, is that you cannot even compile a suspended function unless you are executing it from a suspended context. So let's take our function with the suspend keyword. Now we know that this function is pure because my function right now, I know that it requires some suspend context in order for the code to compile and to run. Typically in functional programming, execution of pure function that produce side effects is reserved for the end of the world. What the end of the world means, it could be the main function, if you have, I don't know, a console application or a CLI, or in our case, it could be the controller or the handler. So now we have our pure function, we have the composition, but we have another problem. We lost the ability, since we're not currying and partially applying this function anymore, we lost the ability to inject things into it. So we'll have to think differently on how to tackle this problem. And I'm going to use another feature that is in Kotlin, which is called extension functions. But this is not your typical extension function because I'm creating an extension function over some generic type R. And this, you can think of this R as being your environment on which the function is executed. You can see here the where keyword, and the where keyword is specifying the compiler that my generic type R can only be of type DB client, which is cool. Right now I'm using only a DB client inside my function. But what if I have to log things? We usually log things in order to debug our application. So I might want to log if the store of the function was successful or if it didn't. But you can easily add the logger as a dependency to your function, and you can use the logger as well inside it. Since I've talked about Spring, which is a very common framework that we use in our day-to-day job, the DB client is probably something of a user repository. And the user repository usually looks like this, where you have something from Spring data, and inside there you have a bunch of functions. But you should take a step back and think about what your store function has to do. So it has to insert something in the database. And does it really need to know all of this? I would say not. And let's see how we can address this thing as well. So instead of using the user repository, we're going to use something called single abstract method, which will only know how to insert a user inside the database. And instead of using the user repository as a dependency, I'm using the insert user. This is pretty similar to what I've shown you with the partial application. In the configuration part of your application, you can actually do the implementation for this type, for this insert user type. So let's move on. We have our function. We've did everything that we had to do in order to make it use types, to have dependencies, to be pure, and so on. And let's think about our goals. So what we wanted to do is to control the side effects in our application. So safe composition. But how do I signal my business errors? Is it okay to throw exceptions? Well, with Arrow and with Kotlin, it's fine because suspend will give you the same guarantees as an IO. If you throw an exception within a suspension function, it will safely end up in resume with, which is good. But exceptions are not encouraged in functional programming. And we could do the same thing by using something called either. And either is not part of the standard library, it's part of Arrow. And you can think of it as being a pair, and this pair contains the left and the right side. And by convention, on the right side, you put the return values, and on the left side, you put the failures in our system. And either is implemented right biased. So all the operators that are created for this type execute on the right side. And let's see what this means. By putting everything together again, right now we have the register function that goes from an HTTP request to instead of going from an HTTP request to an HTTP response, it goes to an either, because here we are capturing the possible failures within our system. Okay, if you look at this code, you can see now that instead of using and-then to do our composition, we are using an operator called flatmap. And this operator flatmap does exactly what and-then did. And the difference is not that big from what we had previously. We have deserialize, we have validate, we have map to, we have store, we have serialize, and so on. But there's a different way on which we can do this. And instead of using the flat map operator, we are using an either block. And this either block, yeah, I see that the presentation is a bit behind. Sorry about that, I don't know why. So we have the either block here instead of using the flat map operator. And what this allows us to do is to make the code look a lot more imperative. Another important thing with using either blocks is that we have the bind function. And what the bind function does, it's actually extracting the value on the right side, and it's it's assigning it to the variable that we have declared. Another thing that is important when you use either blocks is, okay, what happens when my application fails? So let's assume that our store function would fail and it will produce some error when we try to insert into the database. Maybe the database is down, or I don't know. It doesn't really matter. What actually happens here is that the execution is going to be short-circuited. This is going to be the last line of code that will be executed. And the result of the function would be an either with the left side. And on the left side, we will have something like maybe unable to save user. Okay, so we've put everything together. We've seen how we can achieve all of these things. Now, many frameworks already have support for suspend functions. Spring Framework has very good support. Vertex has very good support. Ktor was built with suspend functions in mind. However, if you cannot use any of these functions, any of these frameworks, you can use coroutine builders, and coroutine builders basically bridge the two worlds. And if you cannot or do not want to use this, you could also create and run coroutines programmatically. So the key takeaways from this talk would be try to use pure functions almost everywhere, because pure functions are deterministic, are a lot easier to test. And yeah, as I've said in the beginning, they remove a lot of the headache we get at runtime. Immutable values make concurrency easier, which is very cool because, yeah, concurrency is a difficult topic, and we need the more help we get on that, the better. The compiler is your best friend if your exceptions are well typed. So try to create types, try to use smart constructors, and your domain will be much safe. And also don't forget everything you know about programming. Usually when you start with functional programming, you hear things like, which I've tried to avoid during this talk, you hear things like monads and category theory and so on. And while all of these concepts are important in functional programming, you can learn them while you do this. And as you can see in Kotlin, you don't really need them as much as you would need them in other pure languages like Haskell. So I guess this is it. Thank you very much. And if there are any questions, I'm very happy to answer them. Thank you.